Oh,
so different. I didn't realize. I didn't see the arrow. Okay, that makes it look.
Okay, that's 4 o'clock. Welcome everyone. So I'm going to start with a small bit of administrative stuff, and then we're going to get started on content. Our exam is going to be next Thursday, I believe, the 12th, 7 to 9 p.m. It's not Thursday.
Oh, it is. I was just.
Okay, cool. All right. Okay, it is the 12th, Thursday. By the way, if any of you have a conflict with the exams, Chloe should reach out to you if she hasn't already. If you have not heard anything from her, you can ping her, and she's in charge of the makeup exam. I'm just writing it. There will be, in fact, 2 different versions of the exam, so if you were planning on cheating, sorry. Unfortunately, I have to write 2 exams, though. One other thing. So I am now going to be giving I've decided to give a second project starting this week. I've already written the written portion. I will be very clear about this. I am very far against assigning homework over break. I do not expect you guys to work on homework over break. I do not want you to work on homework over break. I mean, if you want to, go ahead. But the way it's going to work is that the written portion is going to be assigned this Wednesday until next Wednesday. You can think of it sort of as helping you study for this new topic. And then the coding portion is going to be due a week after break ends. So you're going to have an extra week to work on the coding. If you'd like to work on it over break, I will give you the coding portion ahead of time, so you can work on it if you'd like. Question? Yes. Also, I've been getting a lot of questions asking for study guides, asking for exact topics of what's going to be on the exam. Just to broadly answer that in person, what's going to be on the exam? Everything we've covered in the class. You can break down each of the lectures, like the titles that I gave each one of the lectures. Those are the topics on the exam. Exactly how it will be formatted and all that is still being decided, but mostly you will be asked to analyze an algorithm, you'll be asked to write an algorithm, prove correctness, and answer some things about runtime, broadly. And I do not have the bandwidth to make more material, unfortunately. I know that everyone would love if I could make a bunch of study guides and stuff, but I just don't have the time to do that. If you want more studying, if you want some extension from the class, go to office hours, please. It's a good place. And the SI sessions. Yeah?
I'm going to have an exam review probably on Tuesday. I'm waiting for them to approve the time. Yeah, I'll announce that once I have that set for sure.
And that. Cool? Cool. All right, we have a lot of material for studying. Also, if you want any other material, if you want to find other slides or anything on any of these topics, there is a lot online. You look online for it. I promise you, all the topics that we've talked about so far, you should be able to find a lot of material on it if you'd like to, along with all the lectures and office hours and all of this. Okay, cool. So now, today, I'm going to start by talking about Dijkstra's. So last class, I overstated the similarity between prims and Dijkstra's, so I want to correct it a little bit, but talk about how similar they are, actually. So the problem with Dijkstra's is we have some sort of graph like this. It can be directed or undirected. In this case, it's undirected. And we'd like to find the shortest path from some node to some other node. We'll start with this version of it. So turns out that if we want to do this, has anyone seen Dijkstra's before? Did you guys cover it in 250 or anything? See a nod yes. Anyone else? Okay, a mixture of yes and no. So I will explain the algorithm, but then you'll probably pretty quickly see the similarity to prims. So the way that this works is that we're going to start with our node S, and we're going to look at the cut between this S and everything else. So we'll look at this cut right here. Right there. And then we're going to add the minimum weighted edge. Let's make this a 1 just for the sake of it. Just so we can say that this one is going to be added. So we're going to add this node first, and we're going to say that that's going to be added here. And then we're going to look at the cut along all of these reds, along with everything else. But the one distinction, so this would now be the cut. And with prims, this would now be the minimum weight edge. But with Dijkstra's, the difference is that we're going to look at this. Actually, I'll make this a 2. I'll say that we added it as 2 just to make this simple. We add also onto all the edges from here the distance to this node. So this is going to be marked as 2, and then all of these edges are going to get a +2 to them. So now if I want to add the minimum weight edge, it'll be this one right here. It'll be this 2. Okay, does that make sense? So as we continue this, I now add this node, and this one is also going to be marked as a 2. And now we're going to look at all the edges along here. So if I now do my new cut, it'll be like so. And this is going to be +2, this is going to be +2. I'm going to add this one. This will make this a 4 now. Okay? And again, I continue like this. These no longer matter. Here I have this, and this will be +4, this will be +4, and you'll see that this is now going to get added as a 6. And then after all of this, we're eventually going to reach this right here is going to be our minimum on our last cut. So our target we can reach with 8 distance using that path right there. Okay? That makes sense? Does anyone notice a byproduct of this process? So we found the shortest path from S to T, source to target if you'd like. Any other byproduct besides finding the shortest path there? Yeah.
We found the cost of the path.
We found the distance of the path. That's true too. Anything else?
On the shortest path.
We found the shortest path from S to any other node. So this process has found the shortest path from S to every single node. In fact, they're now marked with the distance to them on here. Although, one thing I'm going to point out about this is that the bookkeeping for this is actually a little bit difficult. So if I want to find the minimum path from S to every other node, I'm going to need to keep track of all of the edges that I add and what nodes they're to and all of this. And it's a little bit tricky to bookkeep this in an efficient way. So I want you to consider the bookkeeping, like keeping track of all the edges you add, which paths they're a part of, and the overall path to every single one of these nodes. Yeah?
Shouldn't that be 3?
Which one?
The bottom.
Bottom left one, like this one? No, so it added this edge. Yeah. So the difference with this and prims, right? So prims would have added one of these two, and then would have added this one to connect to them. So prims is different with Dijkstra, sorry. It's essentially running prims, but in each one of these steps, we add weights to all of the outgoing edges, dependent on how far the node that they're connected to is from the source. Does that make sense? Okay. Yeah.
Won't it not necessarily?
So if I have it end when I find T, then it wouldn't necessarily. In reality, when we run Dijkstra's, we don't actually have a target node. We are just finding it to all nodes. So we wait until every node has a path to it. Yeah, or every node we can reach.
So basically,
Yes, it's essentially, I think the easier way to think of Dijkstra, this is why I was saying that they are very connected and that they should be taught sort of in tandem, is that it is essentially exactly prims with the one modification that when I'm making one of these cuts, I add the distance from the source to this node to all of the outgoing edges. So the one that I add will guarantee be a shortest path to that new node, because the path from S to here is the shortest possible, and out of all the options of how to get to this one, this is the shortest of those. Does that make sense? Yeah.
can you
Uh,
just the ones in red?
The ones in red, so all of these nodes, so this is a 2, this is a 2. Those are the same as the weights along the edges to them. What that number represents is it represents the distance, like the minimum possible distance from S to each one of these nodes. And that same value is going to be added to outgoing edges across the ST cut. Okay? All right. Make sense? Yeah.
Isn't it a total distance?
Oh, yeah, it is. It is. Yeah, sorry. Yeah, I just wrote a 7 instead of a 6. I think previously I had it different. Yeah. But yeah, that would be 7 at the end. Cool. Any other questions? Okay. Cool. All right. So now we're going to talk about a new graph topic. We got a whole nother graph topic to cover, and it is one of my favorites, actually. I really enjoy this topic, and hopefully all you do too. It is surprisingly useful and surprisingly applicable. So it may seem somewhat arbitrary how I'm defining this, but I promise you it ends up being very useful, and your next project is going to rely on it very heavily to do something pretty interesting. So, we're going to talk about flow networks. Okay? The basic idea of a flow network is that all of our edges in our graph, we're now going to have directed graphs, by the way, so we're only going to have one directional connections, and each one of these edges is going to be given some possible capacity. So instead of having a weight, it's going to have some total capacity. We're going to draw it like so. We're going to say that there's some value out of the total possible capacity along that edge. Okay? And then what we're going to do is we are going to be able to assign values to each one of these. We're going to call those flow values, or F, as long as F is less than or equal to C and is positive. And what we want to do, so the properties of this is that we're going to, one, have some flow and some capacity along each one of these edges in the direction that they're going. And each one of these nodes will contain some amount of inward flow. So let's say this is like I'll call this node X. And there's going to be some amount of inward flow, right? So each one of these have some flow out of their capacity, right? And we're going to say that the total inward flow for X is going to be the sum of the flow from whatever the input node is. So in this case, it's just going to be all the inputs. I'll just write them as in the inputs. I was use this capital I is going to be all the input nodes, right? So the flow is from things to X is going to have to be exactly equal to the flow out of X, okay? So for all the nodes besides a couple, which we'll talk about in a second, there will be some amount of flow in, some amount of flow out, and those have to be equal, okay? So let's say this is like C and D, perhaps, okay? So the flow into the network, I'm going to denote that like the flow from N, where N is an input, to X, has to be equal to the flow out of that node. Then if I want to say for every node in the output, then the flow from X to this node has to be equal to that. Okay? Does this make sense? So all of these have the construction that the flow in has to be equal to the flow out, except for two specific nodes. We're going to have them the source node, which we're going to label S, okay, which can have, again, some capacity, but has no input. There's no inward connections into S. We're going to say this is our source. You can basically think of it as an infinite reservoir of flow. And then we're going to have the output, the T, which in the literature obviously stands for sink. You can think of it as target if you want to remember how to what T is, right? So you may notice, by the way, that these are S and T, very similar to our ST cut. That is because we're going to use a lot of ST cut properties here. Okay? So our overall goal in one of these is that we're going to have some amount of capacity along each one of these edges. So I'm going to label each one of these with some capacity. And our general goal with these networks is we want to assign flow such that we do not break this property and that we maximize the flow into T. Okay? So I'll assign some amount of these. So let's say I have like 2, this is 4, this is 3. I'll draw them with a little dash, say that I have some amount of flow out of that. This one I'll say is 5, and so on. So I want you to think about what the flow that I would assign here to maximize is, and just think about it for a little bit, okay? And I'll ask you in a second. Okay. So, if I want to maximize this flow, right, can I just send 2 flow along here and 4 flow along here? Why not? Oh, actually, one thing I forgot to do. Who wants the bag? Okay, I saw your hand first, so here you go. Okay. Now, anyone want to tell me? Yeah. Where?
The bottom node A.
Exactly. So because the output capacity is only 3, you can think of it generally to think of flow diagrams. We can think of things like pipes, for example. So we can say there's a large pipe here that allows 4 flow through, but then it goes to a narrower pipe, so we can't allow more flow going through that. Ignore water pressure or anything like that. Just say that that is the amount of the maximum pressure that they can allow, perhaps. But there's only so much flow. Another good analogy, actually, that's maybe slightly more apt is roads. So say maybe we have like a four-lane highway, and then it goes to a three-lane highway. We can't allow more cars to go through, then can pass through this. Okay? Again, not a perfect analogy, but gets a picture in your head. So at most, this could be 3 from here. Okay, so at the very most, this could be 3. How about this one? Yeah, so it could be 2 because this has a total capacity of 5. But will they actually be those values in the maximum flow? Anyone want to tell me why? So I don't know what 8 and 7 are talking about.
Like by curves of x, it's 4 and 3.
So that's a, yeah, so these are 4 and 3, I don't know if, so hypothetically we're talking about maxing this out to 2, right, doing as much as we can here, but this one only 3 because it's bottlenecked here. And then when we go here, we would have 5 input to x, and then we can choose how to assign it out, right? So we could say, oh, this one will be 4, this one will be 1, or whatever one of these combinations we want. But then what's the problem? Exactly, we have a bottleneck, right? That's a good bit of imagery to put in your head. We have a bottleneck here where only 1 can pass through each one of these. So, in fact, the amount that I can have from here would be at most 1, meaning that somehow I can only take 2 from here. And there's multiple different ways that I can reassign here. Let's just say that this one is, we have 0 flow going here, and only 2 going through the top. So this would be a maximum flow solution to this problem. Okay? Any questions on this? Yeah.
Okay, so at x you have 5, and is it like you have to split 5?
So it has to be exactly equal. So however much is going in has to be the amount going out. In this, in a maximum flow here, we know because we have this bottleneck down here, only 2 is going to be able to pass through. You will probably notice that the amount of flow going into T has to equal the amount of flow coming out of S, and perhaps you can extrapolate this. Because if I had more flow coming here, at some point this property would need to break. Okay? That makes sense? So, any other questions on this before the quiz? Yeah?
Could you explain
So with this, you can pick any node here, and you can look at it, the B, for example. The flow is this first number, the capacity is the second number. That's a total maximum flow that we could hypothetically pass through it. So you look, the blue, the sum of all the blue here is 2. Sum of all the blue as the output is also 2, right? So the amount of flow that's going in has to be equal to the amount of flow going out. Same with X here, we have 2 coming in from here, 0 coming in from here, and then it is outputting 1 and 1, which is also equal to 2. Make sense? Yeah. So the only nodes that can violate this property are S and T, which are going to be our source and our sink, respectively. Cool? Any other questions on the formulation of maximum flow? Okay. Okay. Yeah. Would it be easier to start from the end and move to the back? Not in any objective way. So in this particular case, it'd be easy to start, let's say, with the bottleneck and then do that. But a bottleneck could have been anywhere. I could have said that there was 1 and 1 output here, and then anything like that. You'll find that there is some sort of relationship between finding the bottleneck and finding the flow, but it isn't necessarily easier from the end to the beginning. They're equivalent problems, actually. Okay? Cool. Yeah?
Wait, so right now
So the only thing with the capacity, so this is one condition, is that the flow has to be equal to the capacity. The other thing is that for any specific node, the flow across any like AB has to be less than or equal to the capacity along that same edge. Okay, that's the only other property that we care about for now. So these are the core properties of a flow network, and then one thing that we would like to do with it, and the overall objective generally when we're doing a flow problem, is we'd like to maximize the total flow into T. And that is equivalent to maximizing the total flow out of S as long as we obey these properties. Okay? Cool. All right. Any last questions before the quiz? Okay, you may begin the quiz.
Not true or false, you have to explain your answer.
It's not about this, it's just post all the quizzes.
I try not to post them ahead of time. You can start talking to neighbors now. That's simple. You'll at least be able to analyze them.
Like the lowest price. So like picture the other still I said I can
Another path. They don't overlap at all. So let's say like, let's say this one's like, I don't know. So let's say they're both like 7, right? This one has like, how do we show that this actually
So I mean, it is actually it's actually there's a little bit more stress. It doesn't matter.
No, I mean, this one
There's no
There's no edges in the max.
Well, I was confused. So yeah, they talked about there being an S. So it just meant any. So okay, I realized there being
From just the two S.
it's a division or you have two sets.
Yeah.
And supposed to all the edge that goes between anything else.
Okay.
So like if you put it like this. Wait, this not like
That wouldn't be.
yeah. So what if I know?
It says the flow always is. I usually just it's like the output is always the package is one. So if I give it between the 2 points, you're always equal to the input or output. Like it must be. It's one of like the problems, like the
Right, but the question is asking like, is everything
equal to the sum of the class.
But if you assign they all have
Every input has to be
It's just like by symmetry, it must.
and that's what the other is.
And in this case, it's
So yeah.
okay. How are you?
Okay, sounds like it's chilling out a little bit. Hopefully you all have answers to all of these. So first up, let's look at the max flow. So max flow, right now we're just doing it by hand. Anyone want to tell me what they are? What's the total max flow? Remember, the max flow like number, the magnitude of the max flow is just the amount of flow going into T. So what's that value first off? Yeah. 19. Now, a question for you. Is the maximum flow always equal to the total capacity of the edges into T? It is not. So, we can have multiple bottlenecks. For example, if I were to change this to 1 and 1 as max capacity, then it's pretty clear that only 2 flow can come out of S, and therefore only 2 flow could go into T. So they do not always need to saturate the edges into the sink, but they happen to in the 2 examples I've done. So apologies for not being super broad there. So, what are some of the values that we could take on here? Anyone? Yeah. Sure, yeah.
So, since the maximum
Case it is, yeah. Both of these are going to be
and then
messed up.
there's multiple do this, what I did, like
Okay.
then that leaves me 3
Alright, cool. Exactly. So that is a valid solution. We also don't need to use the middle edge at all. We can just use the bottom and the top. Both of these are totally valid. Then it would be 12 coming out of the top, 7 coming out of the bottom. There's multiple different solutions. Alright, so now, from here, alright, let's think about the other ones. So, next up, will there always be a saturated edge? How many people think yes? How many people think no? Saturated edge is where the flow, the top number of the fraction, is equal to the bottom number. Yeah. Like, for example here, 15, 15, 12, 12, and 7, 7 are all saturated edges. Right? So, anyone, argument to why that will always exist in a maximum flow? In the back.
For any, there will be at least one change. Any of them are not saturated, you can always just
Exactly. So we can imagine some path from S through whatever nodes, up to T. And if we assume that all of them are not saturated, that is, there exists no saturated edge along here, then none of these capacities will be over n. Let's say all these are n minus 1, just for the sake of it. Whatever these are, I'll say C minus 1 and C instead here. So all of these, if I have that all of them are less than or equal to, the amount of flow is less than or equal to the capacity minus 1, then of course I can add 1 flow to all of them. I know that this path already exists from S to T, so if I add 1 flow to each one of them, then I will have increased the flow. So by contradiction, this is not a max flow. Therefore, a max flow must always have a saturated edge. Does anyone have any other stronger claims about a max flow and saturation? Sure.
The smallest
Not always. Yeah, I did this example right here. Yeah. There may exist a situation where it is, but there also could be some edge that is not even on the path from S to T. That there's no like path from it. Yeah.
The bottleneck's edge.
The bottleneck's edge. So when you say edge, you say bottleneck edge. That's pretty much. It sounds a lot like what he just said. Of the minimum capacity edge would be saturated. Do you have any other thing to say about it?
The bottleneck doesn't necessarily.
So what is it then?
It's just something that essentially like constricts the flow of your movement. Like in the previous diagram, the bottleneck was more.
Okay. Okay. So you're getting at the idea, but you haven't quite actually fully formulated it. Yeah.
I would say like a bottle edge, like
Okay, we're getting closer. We're getting closer, perhaps, but we're not quite there yet. Yeah.
Is the minimum edge connected to the?
Still no. That isn't guaranteed. Need to be saturated. I can make this 11, and I guess in this case it would still be saturated. But there are cases where I could make sure that it's not saturated. Yeah.
If
Okay. So I mean, so from later on, we'll actually see that the flow across each one of these cuts will all be equal. So none of them will be greater than the flow into T. So you're getting at something, a nice idea there, though. It does have to do with our ST cuts. Yeah. Not necessarily either. So I can have something like, just to give you a very quick counterexample, S, let's say that this is out of 10, whatever, then this middle node is out of 1, and then to T is out of 10 also. So this is clearly a bottleneck, right? I can only have one flow maximum here. Neither edges out of S or into T are maximized or are saturated. Yeah, you seem excited.
Isn't that for any ST cut, it must contain?
I actually don't know if that's true. That might be true. Do you know off the top of your head?
If you make the both of them coming from S like 1, and you make both of them going to T 100, then if you cut off the two that are next to T, that's a counterexample.
Oh yeah, there you go. Yeah, no. Yeah, this is actually a counterexample of that. Yeah.
Is it
The minimum ST cut. So what would the minimum ST cut mean?
the bottleneck?
The bottleneck. So anyone? I'm gonna leave this as a hanging question. I'm gonna ask you again after we continue the next two. Okay. So next question. Let that simmer in the back of your mind. There's a very satisfying answer. So can there exist two disjoint maximum flows? That is, where they don't assign flow to any of the same edges. Can that exist? Raise your hand if you think it can. Raise your hand if you think it can't. Okay. It cannot. Anyone feel like explaining why it cannot? Sure, go ahead. Okay.
Naturally, I did not have to think too much about it, so I'm proud of this one. So I said if there's like two disjoint maximum flows, then if you just add them up because they're disjoint, then that's going to give you another maximum flow. So therefore, like via contradiction, the first one can't.
So this is exactly the principle of it. Is if I have one flow, let's say that this is my first maximum flow. Let's say it's just a straight line. If I have another maximum flow like this, and if they are disjoint, right? Then there's nothing stopping me from adding the flow along both of these. There's nothing that stops me from I won't violate either of my constraints by adding the flow along here and the flow along here. Because they're disjoint, they will not use any of the same capacities, meaning they won't interfere with each other at all. And in fact, if they are not both being used maximally, then it is not a maximum flow. So in fact, this cannot exist. We can prove by contradiction that if I have a situation like that, then this flow here cannot be maximum because there is more flow that I could send along the other path. That make sense? Yeah.
what if there's
They can't share an edge. If they're totally disjoint, they don't share any edge. So they'll each have some bottleneck, perhaps, but they won't share a bottleneck. That makes sense? Because they're totally disjoint. The disjointness is what matters there. Question?
What if you had like two different paths that had identical edges, but they were
So I'll give you an example here. So what you're suggesting is a very, very simple example of what you're suggesting here is if I had just S and T connected where this one, I would need an internal node because I can't have multiple things.
A node on top and a node on bottom.
Sure. Let's do this where they're both out of 1, right? Like this, and there's 1 here. 1, 1. So this, I can send one here, and I can send 1 here. The problem is that they're not maximum, because I could send 1 to both of them, because they don't share any edges. So the problem isn't with their existing possible disjoint paths where I could send flow. The problem is that those are not maximum, because if they're disjoint, I can send them along both. Make sense? Cool. Any other questions on this one? Okay. Now the slightly more involved one is for any flow assignment. This is not necessarily maximum flow, although flow and capacity both have to be greater than or equal to 0. Capacity has to be strictly greater than 0, actually, but flow has to be greater than or equal to 0. It can't be negative. Does there exist, or does every ST cut, every possible ST cut, and to clarify here, ST cuts, S has to be on the S side and T has to be on the T side. That's why we call them ST cuts. In those cases, is the flow across every possible ST cut the same? Who thinks it is? Who thinks it isn't? Okay. It is always the same. Anyone wants to explain? Yeah. Yeah, so this is the conceptual answer to it is if I make any ST cut, I'll use the example that maybe feels like a counterexample to people. That cut right there, right? The amount of flow that crosses any of these cuts has to be the entire flow. If that were not the case, then I would actually be breaking this property. I'm going to maybe leave it as an exercise to you to prove that, but yeah.
To clarify, you mean the net flow, right? So we're counting this.
Yes, so I was about to say that, yeah. So to clarify also what it means to have flow across an edge, we have some flow that goes from S to T. So we have this 15 is flowing from S to T. This 7 is flowing from S to T. But this 3 is flowing from T to S. So the total the total flow across this ST cut is going to be the sum of all of the flow from S to T. I'll just do so flow from S to T. I'll do it like that just to shorthand. And then it's going to be minus the flow from T to S is how we're going to calculate the flow across that cut. Okay? Yeah. Sure, let's do it. So this is S, and the rest is T. So S has to be on the S side.
Oh, okay.
Yeah. That's why it's breaking. Yeah. No, if you have, I promise you, if you always have S on one side and T on the other side, you'll always be having flow. If I do any other one of those where S and T are on the same side, it'll always have a flow of 0. Yeah, you can think about that if you like. Okay, cool. All right, so every single possible ST cut will have to be equal, right? We'll have to have the same amount of flow going through here. Now with that revelation, let's go back to our previous question. What can I say about saturated edges and ST cuts in a maximum flow? I want everyone to think about this. I want someone to be able to come up with the answer here. So there's something stronger I can say than just that one edge is saturated. There's something a little bit stronger I can say. I'll give everyone a second to think about it again. Now, why don't you all discuss with your neighbors? I'm going to give you a couple of minutes. See if you can figure this out. It'll be enlightening if you can.
Is that like blue throwing?
Yeah, that's it. Yeah, so S is on the left hand side. I wrote S there as it's not S. Got it. It won't be that easy. Then you equal to the like you subtract the ones going to TS.
This has to be something that we I don't know what person is.
Also, none of the outputs
always happens.
All right. Anyone got any claims? Anyone got any claims? Back there. Okay. No. Sorry, we already covered that counterexample. The counterexample was just something like this, like S, then like 100, then 1, then 100 to T. Something like this, right? This cut is not going to be saturated. Yeah. Cool. Yeah.
There must exist an ST cut such that.
So there must exist some ST cut such that all of its edges are saturated. Let's take a look at this. Is it true? Yes, in this example it's true. So we have this cut right here, where all the edges along it are saturated. Now, will there always exist some edge like this? Or some ST cut like this?
Yeah.
Who thinks there will be? So there will, in fact, always be one of those. I think there's another proof I'm going to leave to you guys to consider and maybe try to prove on your own. If there was no such ST cut, then we know that we can add one more flow because every single ST cut can allow one more flow across at least, so at least one of them must be saturated. Now, can anyone tell me how to find that ST cut? Yeah.
I know the answer. Can you remind me what the question?
So the broad question was just, is there some other property about saturated edges and ST cuts that we can say with certainty? One conclusion here is that there exists at least one ST cut where all forward edges, all edges from S to T, must be fully saturated. And I'm saying there's something even more specific we can say about it. We know which ST cut this is, hypothetically. Can anyone tell me which ST cut this is? So this is good. So that is correct. That it is going to be the so you can. This follows directly from the fact that all of the ST cuts are going to have the same amount of flow, right? So if I have some ST cut, that is fully saturated, then because it's fully saturated, its total capacity is equal to the total maximum flow. Right? Because it's already maximum, we decided it's maximum, and we know that they're saturated, so maximum capacity equals the maximum flow in this case of this ST cut. And I've heard a couple people shout out some suggestions. Any other properties about this ST cut? So you're saying it's a bottleneck. I'm going to need to be more specific than that. What does it mean to be the bottleneck? I'm not calling either of you guys. Just answers. What does it mean to be the bottleneck? Yeah. What value? So the flow is going to be equal to across every SC cut. We already proved that. You're very close though. Yeah, in the back. It is going to be the ST cut with the minimum capacity, which is a formalization of this idea of a bottleneck. So the sum of all of the capacity from the S side to the T side, if I add up all these edges and I sum all of their capacity, then there exists some edge, some SC cut, so along this SC cut, if the capacity is minimum out of every possible ST cut, then I know that for the maximum flow, both it will be totally saturated and its total capacity will be equal to the maximum flow. Okay? How do people feel about this? Does this feel intuitive? I see a vigorous shake no in a few places, but some shakes yes. So very much we can think of this like the bottleneck, right? So as before, we can think of this as sort of bottleneck of this graph. If it were to be that I had a higher capacity here, if I increase some capacity here, then I know because everything else is not saturated already, if it's uniquely minimum, then I know that I can force more flow through it. That make sense? Okay? Okay? Is everyone okay with that? Yeah, so this is going to be one of the main results we have of maximum flow is that it is equivalent, finding the total, like absolute maximum flow is equivalent to finding the ST cut with minimum total capacity from S to T. Does sit okay with everyone? Okay, okay. Yeah, question.
We're going back to what we already did. All of them have
Yep.
Can you just remind me? I know it is yes.
Yeah, so I've just said intuitively, I haven't actually given a proof of this, but we've said that every ST cut is going to have the same amount of flow or it's going to have the same amount of flow crossing it as every other ST cut. Basically, I'm going to give you, again, just a little sketch of this proof. If people really want this proof, I can give it to you on Wednesday. You may notice I lost my notebook, so I actually don't have any of my notes, so I don't want to do any proving on the board. It's a fairly straightforward proof. It follows from this property, basically. So if I have any ST cut, let's say that I have this ST cut right here, right? Let's say I have this ST cut right here, and it has some flow crossing it. In this case, it has a flow of 19, as to all of them. So if this was 19, and then I were to look at some other ST cut, let me use a different color just to make this a little bit more clear. So I looked at this ST cut, okay, something like this. This is a flow of 19. If I had a different ST cut, right, perhaps I can find a single ST cut. Maybe I can do something like this ST cut right here. And if this does not equal this, right, if this 19 does not equal whatever value that is, then you can pretty easily show that this property is being violated. So basically you can just swap one node, and if those two are not equal now, then it does not stand. This isn't sufficient to do this proof, but it shows you a little bit of how we can go about doing it. Does that make sense? Cool. Yeah, one other way that I tend to like to consider these graphs, when I'm doing an SC cut, you can think of it basically like you have one giant S node that has connections to one giant T node. And it can show you a few things about it. Basically, like if I were to consider this ST cut and I had some flow backwards, right? This has some capacity, right? We know that there exists some way where the maximum flow sends only forward and none backwards. And you can start to get some properties of ST cuts and max flows by just considering it like that. Just something for you to think about. Okay, nice. How about this? Okay. Here's another little question for you on flow. Let me see how much time we have. We'll talk a little bit about other stuff, but I'm going to ask you another question. So if I were to have some backwards connection like this, with some possible capacity, doesn't matter what it is, some possible capacity, is it possible that there exists a maximum flow, in which case there is some capacity that goes back to S? Don't think necessarily of this graph, but if I have some connection from any node back to S, does there exist a maximum flow that uses that edge, that sends any flow along that edge? Is it possible for that edge to have any flow in it if there's a maximum flow? Yeah? Think for a second. Think for a second. I was asking a side question. Yeah. Okay. Who thinks that there exists some way that there could be flow going? Oh, you have a question? Sure. Oh, no? No. Okay. Who thinks that there is some way that there exists a maximum flow where I'm sending flow back to S? Okay. Who thinks that there does not exist a way, that it wouldn't be maximum? So there does, in fact, exist ways for this to happen. So in this example, like for this particular one, I could do something like this. So instead of doing that one, that was a little bit of a throwing you off. If I had something like this with 6 capacity going backwards, I can saturate this, make this 10, and then we're good. Right? That would still be a maximum flow. I just have this cycle now, and it's a useless cycle. Now, same question. Does there always exist a maximum flow where there exists whatever edges back into S that we want, such that all of them have 0 flow, necessarily have 0 flow? So if I have some of these edges, will there always exist a maximum flow where all of those edges have 0 flow? Yes or no?
Which edges have 0 flow?
The ones into S.
The backward one.
The backwards one into S. So does there always exist one? Raise your hand if you think that there does. Okay, raise your hand if you think there isn't. Doing it in the wrong order to get hands. So yes, of course, when we have a cycle in our flow graph, we can always remove our cycle by removing all of the flow that is traveling along that cycle. In this particular case, it would go back to the original, and this would be 0 flow. Okay, so that's one thing that we can think about, is that our flow answer is always going to have no cycles in it. All right, there will always be a maximum flow with no cycles. Sorry, that's being more specific. Likewise, by the way, actually as part of the normal formulation of a flow network, we actually are going to disallow any connections into S or out of T. We know that there will always be an equivalent version that has no inputs into S or outputs out of T, so we're just going to remove them. They will not change our maximum flow answer. Yes? So flow networks are not acyclic. I mean, I can very easily add a connection here to make it cyclic. But the flow themselves, there always exists some maximum flow that is acyclic. That makes sense? So we never need to have flow go in a circle. It doesn't actually break any properties of ours, but we will find later on that getting a maximum flow like that is also slower. So we want to remove the cycles if we can. Yeah. What are flow networks used for? That's a nice transition. Why don't I ask you guys that question? Can anyone think of any problem that we could formulate this way? Traffic, I think, is lots of them are a good example. I think traffic is a very clear example. Let's imagine that we are Google Maps. Okay. So let's imagine that we're Google Maps or Apple Maps or whatever. I don't care. I haven't been hired by Google yet, so I'm not too touched. So we can say that we have some starting location. Let's say we have a bunch of people who are coming from outside the city. They're going along some highway that goes into, let's say there's some big highway. Let's say 1,000 cars per second can travel along this highway, whatever. They get to the town, and then there's multiple roads out of that town, or out of this junction, right? Maybe this one is like 50, this one is 100, and this one is 200, something like that. Okay? But then it turns out, this can connect back to here, perhaps, with some, maybe we have some setup like this. Maybe this one can even connect back to this one. So we have a cycle in our graph, if you like. But let's say that out of all of these, right, this one has, goes through some alleyway down the way, right? So now it has a little, has a bottleneck of some road of 10. Let's say this one continues as just a highway through the city or whatever. And this one perhaps then goes to another large highway with 1,000, something like that. And then all of these connect to the going outside the city with some capacities. So you can imagine it's actually pretty clear that like the correlation between our flow network and all this will say that these are all the people traveling through the city, and there's multiple different routes they could take. Now, a sort of naive solution to a problem like this, as was in early maps days, is we just find the shortest path. And we say, all of these cars go through the shortest path, but then we end up getting bottlenecked by whatever that shortest path is, or whatever. I mean, shortest path is specifically bad here, but let's say the path that can take the most cars, let's say. So we'll say we'll pick one path, which is like this middle one, and we'll saturate it with 100 cars and say, everyone go that way, right? And then we end up getting heavily bottlenecked, and then the slowdown here becomes only 100 cars to pass through here because they all get bottlenecked because I'm sending with my GPS system all of my cars right here through the middle. And it turns out that using something like flow, we can send cars in different directions. So maybe I can send, I don't know how many I can actually send. I haven't thought about it too much, but let's say I can send 50 here. Let's say I can send 200. Yeah, I can send 200 here because they're going to go along this edge, which I didn't label, but I'll say is out of 200. Sure. I'll send 190 this way, actually. 90 this way. I can send them on different routes, and although this may be slower for some people, right? Like some of the people are not taking the optimal route, as in the one that can let the most traffic through, or is fastest in the real world. We actually care about that. What we end up seeing is that the overall throughput has increased now. Now I'm allowing 350 through here, and it turns out the entire system is faster for it. So this is one of those things that if you have ever wondered why sometimes Google Maps will send you some ways, sometimes it will send you a different way, that's why. Is because what they're doing is they're not maximizing your specific duration for your drive. They're maximizing everyone's. And it can be formulated as a flow problem. I know I've given sort of have a relationship between time and the amount of throughput of these cars. We can imagine the relationship between them. All right? Yeah.
Is this important for like
It's important for a lot of things. So this sort of formulation is extremely broadly applicable, actually. So I will get a little bit outside the scope of today's lecture, and I'll say that a lot of things can be represented as flow. There's a surprising amount of things that can be represented as flow, where the solution to the problem is a maximized flow problem, and there are very, very many problems that can be represented as sort of a tuple of capacities. So if I wanted to say there is some amount of like green capacity and some amount of red capacity along each one of these edges, and I want to maximize green and red flows simultaneously, a lot of things can be represented like that. And that is a huge, broad category of problems. We're not going to talk about that very much in this class. That's why I'm saying it's a little bit out of scope. But just to give you some justification, flow, tremendously important. And in fact, our project 2 is going to use flow to do image segmentation. So if anyone knows what image segmentation is, we're going to be separating the foreground and the background of an image using flow. So many applications, many applications. I think one of the most natural ways we're also going to see one in discussion. We'll see more next Wednesday. I'm just going to introduce another like classic formulation of a problem that is solvable by flow. We can think of supply chains. Supply chains is another very classic one of these. So you can imagine, instead of thinking of it as highways, which I think is a pretty good justification, if you look it up online, you'll find this formulation a lot. We say that we have some factories, okay? We say I have some factories, factory 1, factory 2, factory 3, whatever, and they can produce some amount of their respective goods, and they can send them to some storehouses, which have some sort of capacity. But they're only able to send some amount to each one of these. Let's say that this middle one can't even send to S2, so it can only send to S1 and S3, and F1 can only send to F1 and S2, let's say. Right, so each one of these factories can only ship to certain storehouses. Each storehouse can only have some sort of capacity, and we want to maximize the amount of product that we can send to stores, or that we can store in our storehouses. I have not fully formulated it for you, by the way. We will, you'll notice there's no S&T and all of that. You can consider how we might do that, how we could finish this formulation, how I could have the extra conditions of, I have some amount of goods I can ship from F1 to S1, but how do I add the extra constraint of how much F1 can produce? And likewise, how can I add the extra constraint of how much S1 can store? Right? Adding these extra constraints and figuring out how to take this problem, although I've made it somewhat of a graph, but how to take this problem and turn it into a flow problem is one of the most important things about flow networks, actually. We're going to talk a little bit about the theory and talk about algorithms for finding max flow, but by and large, the most important thing for you to get out of flow is figuring out how I can take a problem and turn it into a flow problem. Because we're going to have a lot of routine ways to solve flow, and this is actually a very important concept in general in algorithms, is finding some very nice optimized solution to some problem and converting other problems into that type of problem. We'll talk about this at length later on in the class, but I just want you to think about it, to consider how you could formulate this problem. And I think with that, you guys are packing up. I think it's fine. Yeah, let's end. I think a couple minutes early. That's fine by me. All right, go home. Go home. Oh, by the way, actually, real quick, this quiz, I put the due date, or I put the submission time as like an hour from now. Submit it now. Cool. All right. Yeah. How much do we have left? Just the other guy. Okay. Hello.
Reviews.
You have reviews of me? Is it, okay, sure.
I really enjoyed the class with you today.
Okay.
I think the class was very engaged today.
Okay.
I enjoyed the discussion, and that says a lot because I came back from 2 classes, 2 meetings, and I have my brain.
Okay, cool. Well, I'm glad. Thank you for the the approval.
No, because I was realizing that this is the first time I've seen so many kids of our age not be on their phone, just actually engaged.
Yeah, you gotta kind of
Answer
force it.
questions.
Thank you so much.
So good on you. And also,
Yeah.
so I didn't update my written part to coincide with the code part.
Okay.
So I'm
You
gonna take
butter
another
me up,
day,
and then
I
you come
guess.
with the real question.
I guess I'm gonna take another look.
So they don't need to match, actually.
They don't?
They don't need to match.
Yeah, because I was
As
so
long-
proud
as
of my
long as-
written part, but my code part was just not it.
Yeah, as long as the written part, I mean, you'll sort of get hit on correctness on both of them in a way. So like.
okay, then I don't want to update it.
Okay. No problem.
Bye.
Hi.
Oh, no.
So I do have late submission up until midnight. We'll allow you to submit the bonuses later. Cool. I just want to get in the habit of not having people do the entire thing later. But I think it's fine. It's fine. You submit it when you can.
Yes, I'll announce it. That's also
Yeah. So Chloe is the one to talk to about that. She's going to be running the midterm conflict thing. If you haven't heard from her or you didn't register with the registrar, make a Piazza post about it and include your email and stuff so she can contact you. Cool. It'll be on Tuesday. Cool.
Okay, so my maze generator program was like very complex.
Okay.
And I kind of just converted to pseudocode, but it's like 2 pages long. Is that too long for people?
It's okay. I mean, it's too long for good pseudocode, but it's fine grade-wise.
Yeah, I ran out of time. I was like, oh, I have 2 hours left to like write the pseudocode and sort it out, but like I ended up like running to a bug that took super long to fix.
Yeah. No, try with this next assignment. Try pseudocode first, as best you can. Yeah.
Because my algorithm kind of changed a lot because I figured out
that'll
like
happen.
growing
That's why I
out-
allow you to change them. But
Yeah, because I figured out growing out the path with the onion thing was like broke too easily, so I kind of changed this. I kind of grew out like a maze with like entrances, and then I connected them afterwards.
Yeah.
And then I randomized the paths, and that was a lot easier.
Yeah.
But I'm pretty happy with it.
Okay, cool. I'm glad you're happy with it. Are you trying this problem or what?
I think you set your start here and then you give each of these capacity equal to the amount that we're going to produce.
We just got done with
And then you set your sink over here.
BFS
And set that equal to the amount that you can store in your factory.
and now we're doing like
And then you maximize the flow and then it should sort out this. You give all of these zero ones the amount that they can ship, or if they can ship an infinite amount to each factory.
Oh no. Yeah, so it's
covered in tools.
the same example.
I was
Yeah. Because you're getting flow intuitively. Good luck with the project. The project is a lot more complicated. It's actually, in terms of using flow, it's not that much more complicated, but there's sort of two parts of it. One, the formulation of it is kind of more difficult for the thing. I want to give you an interesting project, and all of the like super simple flow formulations are not interesting enough. So I went with image segmentation, which should be fun. Should be a cool project. But two, finding the max flow quickly is actually surprisingly difficult. So finding it at all is not that difficult. Finding it quickly is difficult.
I think
We're going to go through algorithms for it in the next couple days, next couple lectures.
Because I think the thing I wrote is very slow because I have to only find a path and then along that path add one flow to it and then just keep doing that over again. I also realized that I can
AI
find
could
cycles.
simply just mean like a search.
Yeah, so it will always add a flow. It'll always add a flow. But you can write a proof for this, but it'll always add one flow at least at a time. But that means that your runtime is going to be the DFS search times the maximum capacity. Yep. Or times the flow, really. Yeah. So it can be really bad. This, by the way, called